It's the real thing. So, Unit 5, the properties of petroleum and natural gas. I love this unit. Unfortunately, I got to be honest, I only uploaded the PowerPoint and PDF this morning, so some of you probably don't have this printed. I know most of you guys might not print your notes anyways. It's not really a big deal. You can just follow along for today. This chapter doesn't have any naming. There's no calculations. We're just going to discuss and talk about what organic chemistry means when it comes to petroleum and petroleum products. Really cool unit. The title, as Naeem said, says it all. So, chapter 5, we're going to start with definitions. We'll get into some sources of hydrocarbons. Then we get into the cool stuff: distillation, fractional distillation, cracking, alkylation, all sorts of different reactions you might see in industry. Then we get into some thermal and physical properties, and then my personal favorite chapter or section, surfactants and emulsions. This is a timely chapter because it's all about soap, and you've been using a lot of soap since March, I would imagine. So that's a good chapter. And then the last one might be maybe the most useful for you, chemical corrosion inhibitors. So like, how do we stop corrosion from happening? Huge billion-dollar problem in engineering industry is corrosion. So this is like the unit of all units. And again, good news for you guys, there's no naming, no math, no nothing, just listening and learning. Easy. All right, so this will be a little bit boring today. I do apologize because the first section is literally definitions. Most of these definitions you guys have learned in other courses. So I am going to go a little quick through some of these. Like you can see, it's only about 10 slides, so I'll go a little quick. All right, definition number 1, natural gas. This is, if you're living in this country, one of the most important resources that we have, natural gas. You guys might have heard of this in your other courses, typically as initials, or I guess an acronym, LNG. Liquefied natural gas. From research I did a few years ago, Qatar is the #1 global exporter of natural gas. Up to 70% of the world's supply comes from this tiny country. Incredible. So for the economy, you know, for you guys, your future careers might be in LNG. So natural gas is obviously naturally occurring. It's a gas, which means it's low number of hydrocarbons. So like, low number of carbons, like methane, ethane. And it could have a small percentage of kind of impurities like carbon dioxide, nitrogen, sulfides, or even helium. But typically natural gas is naturally occurring hydrocarbons at the low end of the chain. So methane or ethane. It's just like all hydrocarbons or petroleum products, it's not renewable. So it's not a renewable resource. You've probably heard about that, you know, learning about petroleum products. There is a finite amount on Earth. We are not going to run out of it anytime soon, but unlike sunlight, for example, there is a finite amount. Natural gas is used all over the world for heating, cooking, generating electricity. There are cars that run on natural gas. There are homes that are heated with natural gas. And again, this is why it's such a powerhouse in the Middle Eastern, or specifically Qatar's economy. It's shipped to the United States, Russia, China, all over the world to be used for cooking or heating or any type of electricity generation. Pretty cool, pretty important chemical. And also, I guess I should mention, not only is it used as energy, it's used as a precursor or a reactant in making polymers. So, I mean, natural gas is such an important chemical in everyday life all over the world, between energy sources, making plastics, making pharmaceuticals. I mean, it's used all over the world. So, natural gas extraction by country. Now, I love this image. Unfortunately, You can barely see Qatar there, right? You can just kind of see it hiding away there. It is very dark blue on the graph. And what that means is the darker the blue, the more the country extracts natural gas. So you can see North America, Canada, and United States especially. Not Mexico's a little less, but USA and Canada, very high. But really not a fair comparison, is it? Because look at the size of Canada or Russia compared to Qatar. So the fact that this country is #1 speaks for how much is here. It's incredible compared to the size of Canada, Russia, India, all these countries. There's so much. If you guys were ever wondering, I've never really showed you a map of Canada, but I am from right here. That's where I'm from. And where I'm from is very similar to this country in the sense that a lot of the oil and gas is offshore. For me, it would be in the Atlantic Ocean. Here, it's in the Gulf. But for me, like I can't really zoom in, but I'm here right on the edge of this little island. And in the Atlantic Ocean, that we have offshore supplies. Now, we don't do a lot of natural gas. We would do more of the crude oil extraction, but still pretty interesting. All right, now obviously you do not need to memorize this graph. I'm not going to ask you which countries export the most, but I mean, the simple answer is North America, Russia, China, or the Middle East are very, very high. Even South America down here is pretty high. But nothing beats the Middle East and North America. That's a funny question. I have, well, obviously where I live, I have Wi-Fi, but out on the oil rigs, they use satellite internet. And I mean, that's an interesting question because a lot of my friends and family work in oil and gas in Canada, and especially offshore, their internet is pretty iffy. Like trying to Skype or Google Duo or FaceTime someone offshore, it's not really a good option. Like a lot of my friends who work offshore are big video game players and they can't play online games. But you can send an email out there. You can check your Facebook, but as of now, I think the level of internet quality is a bit low out there. Yeah, exactly. Okay, so let's do 3 more definitions and then we'll kind of get into something a little bit more interesting. Okay, so natural gas, obviously a big product for this country. Crude oil, another big product here, not as much as natural gas. This is kind of what you think about when you think about petroleum. When you watch a movie or some old TV shows where they're discovering oil in the ground and it comes up this thick, black, syrupy, almost like honey or molasses type of substance, that's your crude oil. Crude oil is naturally occurring. It's unrefined. So we don't use it typically in real life unless we've refined it. And it contains hundreds, if not thousands, of different types of compounds. Hydrocarbons ranging from 2, 3, 4 carbons up to 600 to 700 carbons. Crude oil is a incredibly complex substance. It's not just a chemical. It is a mixture of hundreds, if not thousands, of different chemicals. Crude oil, you guys know this, I'm sure you've learned about it in other courses. We use crude oil to be refined to make petrol. We call it gasoline in Canada, diesel, other petrochemicals, so octane, butane, propane, crazy polymers, low density, high density polymers. They all come from crude oil. Again, a very complex mixture of hydrocarbons. So a product of crude oil would be petrochemicals. Petrochemicals are chemicals that are, sorry, my computer just asked me to restart itself. Petrochemicals are products obtained from petroleum through the refining process. I'm going to assume you've heard of refining at some point in this program at the college, but if you're unsure, refining is like purifying or selecting hydrocarbons from crude oil. So it's like separating crude oil into more pure hydrocarbons. So, yeah, sorry, I got a message in the chat there. Just let me read that. I am kind of emphasizing the numbers, and you'll see this later, not today, but wink, wink, wink. When we talk about petrochemical processes, in particular, fractional distillation, I'm going to go real deep in my notes and just give you like a little hint, a little foreshadowing. Cough, cough, wink, wink, slide 47. Can you look at that slide and see the number of carbons and the different names of the chemicals? So from lubricants to kerosene to gases, I'm definitely going to focus on the number of carbons later, but that's a future problem. So let's go back. But Naim did bring up a good question. I did emphasize the numbers because we will come back to that later, probably next week. All right, so chemical compounds made from petroleum can also be obtained from other sources. So it doesn't need to be crude oil. It could be from coal, natural gas, even things like in modern times, they're using natural substances like corn, sugarcane to isolate the carbon and make chemical compounds. So, you know, as we kind of advance in more environmentally friendly methods, you might see more chemicals being made from other carbon compounds, but it's all the same. Crude oil is just made from dead living organisms, dead animals, plants that were buried under the surface. So when I say we might make petrochemicals from something like corn or sugarcane, we're just skipping the middleman. We're skipping millions and millions of years of conversion and just doing it ourselves. It's a pretty interesting field, I must say. This we'll get into later, but this is a term or two terms you might have heard in another course. We can classify petrochemicals in two ways: olefins and aromatics. Now, aromatics you've heard of in chapters 1 and 4. Aromatics have a benzene ring. Olefins are everything else. So ethylene, propylene, ethene, methene, or not methane, no such thing as that, propene, pentene. These are two petrochemical classes, and we'll talk a little bit more about that later. This whole first section, I guess, is kind of like foreshadowing or getting us ready for what's coming. All right, the last part of chapter, or section 1, sorry, is a definition you might not have heard of in other courses. You might have. I'm not exactly familiar with all of your courses, but if you could see my face right now, wink, wink, this is a good one to know. Octane number. Octane rating or octane number is typically listed at the fuel pump. I know now, okay, embarrassing. I don't drive here, so I've never gotten gas here. But back in Canada, when we get petrol, or we call it gasoline, there's an octane rating at the pump. So when you guys get gas here and you pick the grade of petrol, you know, so there's premium, there's standard, or whatever they call it. Silver gold. Silver gold, they call it here. Thank you. They're different octane ratings. The higher the rating, so again, back home, we would say like, you know, regular, and then there's premium. Here, there's silver and gold. The gold would have a higher octane number. What does that mean? Well, the octane number is a measure of the performance that an engine or aviation fuel would get. In simple chemistry terms, I guess that I shouldn't say simple chemistry terms, but in chemistry terms, that's fuel efficiency. How efficient does that octane, petrol, or gasoline burn? The more efficient it burns, the more complete the combustion is, the higher the octane number is. And in terms of an engine, the more that fuel can be compressed without igniting, the higher its rating is. All of this links to how efficient, how much energy, how many joules will you get from burning the octane. The higher the number, the more energy you get. Again, in simple words, you guys just need to know that the octane rating is a measurement of how a fuel performs. The higher, the better. So again, if you guys are pumping silver, it doesn't have quite the rating as gold. What do you need to know from this slide? Okay, so talking about petrol, or again, I say gasoline engines versus diesel. Diesel is not considered as quite as a clean burning fuel as petrol products. And that's because diesel has a lower octane number. So a lot of diesel engines, you'll notice the smoke coming from them is black. It's you know, the pollution from a diesel engine typically, and especially in older cars, is a lot higher. And that's because diesel would have a lower octane number, a lower efficiency than petrol. So when I say lower, I mean compared to petrol. Takes a lot for me to say petrol. Again, as someone who's never driven a car in this country, we always call it gasoline. So anyways, if you ever hear me say gasoline, I promise you I mean petrol. That's it. That's a couple terms that you'll need to know. So just review. These could be good fill in the blank or multiple choice type questions you will see. Natural gas, crude oil, petrochemicals, and octane number are all really good terms you might need to know. I have a sneaky feeling, and I probably shouldn't say this on a YouTube recording because it's going to go public, but I have a weird feeling that your final might be online. It might be. I cannot confirm it. As of now, they've told me that they won't be online. But if your final was online, these are some slides you would definitely want to bookmark or note. All right, almost done. This is a little bit more dry than some of the other chapters. But what I would love to do is to explain distillation and fractional distillation, and we are done for today. Now, this is weird because in lab 3, which was literally a month ago, we did a distillation. In lab 5, which was last week, we did a fractional distillation. And I'm only explaining what they are now. That's just the nature of this course. It's not until the end we talk about 2 of the most important chemical procedures or lab procedures used in oil and gas today. So section 5.2 to 5.9 is actually a pretty small section, and it covers sources of hydrocarbon and different processes involved in hydrocarbon production. I know a lot of my students, especially in 2420, come from the industry. You've worked there before and you're back in school. A lot of these terms or processes you guys have probably heard of or done, if not in CNA, at work. If you've done a work term or you've worked anywhere with like RASGAS or QP, you've heard of a lot of this before. So hydrocarbons, also called fossil fuels, they come from sedimentary rock in the Earth's surface, and we typically find them, like I mentioned, natural gas, coal, or crude oil. Well, when we find these as crude oil, which is, you know, what offshore is what you typically find, we cannot use the crude oil until it's been processed. And the simple way to explain the process is just by distillation. But what's actually used in, you know, modern refineries is fractional distillation. I would like to explain to you today, wink, wink, the difference between a simple distillation and a fractional distillation. And all of you who have done labs 3 and 5 should already know the answer to this. Distillation is a chemical or a lab technique. And I've done 100 distillations in my life. I've never done a fractional distillation until I came here, because in the average chemistry lab, you know, first, second, third year courses, you would just distillate simply. The process of distillation is so easy, and I don't know why this slide makes it sound so complicated. It is boiling a substance and separating it based on the boiling points. So if you have a mixture of liquids and you boil that mixture, they will separate based on their boiling points. It's as simple as that. The lowest boiling point comes off first as a vapor. And if you can collect that vapor, you have done a distillation, full stop. That's what distillation is. So simple. It's amazing that it works, but it really does. So the process of separating components from a liquid mixture by using selective boiling is your fancy, fancy definition. But really, again, all it is you boil a mixture and you collect the vapors. And by, like what we did in the lab, by measuring or really focusing on the temperature, if you watch that graph, you can tell what chemical or what compound you're getting as a vapor. Let me just kind of open up a blank slide to kind of explain that. Remember, in our labs, if we measured temperature over time and we had a mixture, wherever you see the flat part of that graph, oops, sorry guys, I got to do that again. Wherever you see the flat part of this graph, you are essentially extracting a pure component. So this would be like component A, this would be component B, and this would be component C. And if you went back and looked at the temperatures of these components, you could tell if it was something like, say, pentane or hexane or cyclobutane. You would typically use a data book for this. But yeah, any flat point on a distillation curve is representing a phase change where a component is coming off. So it's not enough to say we just boil it. You also have to very carefully monitor the temperatures that you are reading in the distillation. All right, cool. So this is our distillation apparatus that we did in lab 3. We have a round bottom flask with your mixture in it, and we have a hot plate. Here we have a thermometer that measures our temperature. This tube here is called the condenser. We fill the condenser with cold water that help it turn back into a liquid, and we collect our sample over here. You are not expected to label a distillation apparatus, but it's good to know how it works. So we heat up this crazy chemical here. It turns into a gas. The gas travels down this tube where it's cold, and it condenses, and then it gets collected as liquid form over here. Pretty cool. So distillation, you can have a essentially complete separation. You can be, get perfectly pure components. Sometimes when your components are close to each other, it might not be as pure, which brings me to the last part of today, fractional distillation. If your boiling points are close to each other, it might not be a good, perfect separation. This is where we would use fractional distillation, which I'll explain in a minute, and we're done. So just to kind of finish off this distillation topic, in the fossil fuel industry, we typically use fractional distillation. You can stabilize oil by doing a quick distillation, which makes it safer for storage and transport. But in really, really perfect refining, I want to say refining situations, but in like, a pure refinery, you would use fractional distillation. So regular distillation is typically used to stabilize your oil product, kind of like a quick and dirty separation, so you can ship that product around. But when it comes to perfect refining, you're going to use these products for polymers or fuel sources or pharmaceuticals, you would use fractional distillation. And if any of you, I'm just going to skip ahead a couple slides, have seen something that looks like this somewhere in Qatar, or maybe in your notes or in another course or a book or a video.
Why should we use a picture like that in your PowerPoint for computers?
Yeah, you would. And so I just heard from a colleague that, you might have used this in your computer class. What's the name of that class?
MC something.
MC something. You did a computer course. You guys might have already done this before. This is a fractional distillation column. So now in the lab, we're not going to use big giant metal tubes and containers with giant pipes coming from them. We use very small glassware, but you saw this in lab 5. So wink, wink. Why do you use a fractional distillation column instead of a simple distillation column? Well, boiling points of complex mixtures can be very close to each other. I don't have the numbers at the top of my head, but like the difference between, say, hexane and heptane, or even like pentane and cyclopentane, might only be 10, 15 degrees Celsius. And your separation might not be pure in a simple distillation. So fractional distillation helps to separate components that are close together in boiling points. And I'm going to explain why it works. I already did this in lab 5, but let me just check the chat here. Yeah, so Naeem mentioned that you did that NC course with Miss Sarah Lee. I don't think she's at the college anymore, but I know that her and other communications instructors taught that. So anybody who did MC with any of the communications instructors probably have seen a fractional distillation column. And Naeem actually brings up another really good point that I'm kind of skipping over. And I just did this in chemistry 1120. The problem with these chemicals, and I really should have brought this up, thank you, Naeem, is that they're miscible. Miscible means mixable. If petroleum products were not miscible, like if crude oil wasn't miscible, you could just separate them using gravity, using a separatory funnel like we did in lab 2. We can't use gravity or a separatory funnel. Again, you can picture in your kitchen if you mixed water and canola oil, olive oil, even ghee, if it was liquefied, you could separate that with a spoon. You could scoop the oil off the top. But Naeem brings up a really important point. Hydrocarbons are all miscible. They dissolve into one really gross looking solution. And the only way to separate that, well, the easiest way to separate that is to boil it. And they separate based on boiling points. And then Sayud in the chat says, the question is, what's the difference between normal distillation and fractional? And that's what I'm going to get to, and then we're done. And this is something you might want to know. Cough, cough, wink, wink. Sorry. Fractional distillations work on the premise of surface area and time. A fractional distillation column is longer, and the column has lots of little beads or little kind of trays or nodes that stick out into the column. So a fractionating column takes extra time to boil, and it has a lot of surface area inside that column. So as the solution, I'm going to kind of read off my slides here. As the solution to be purified, that's this guy in the round bottom flask, is boiled, the vapors rise up in the column. But the column is 2, 3, 4, 5 times longer than a normal column. So what happens is the hot vapors go up into the column, and then they'll cool down a little bit, and they condense back into a liquid. But as the heat continues to rise, they turn back into a vapor. And this happens over and over and over. It condenses into a liquid, then the heat rises a little more, it turns back into a gas, it'll condense a little higher, turn back into a liquid, then back into a gas, and this happens over and over. And because the condensation and vaporization phase change happens multiple times, it gives the mixture extra time to separate. You can kind of think about it like that. The more time we give this solution to separate, the better the separations will be. So that's the purpose of a fractionating column. The fractionating column allows for multiple condensation and vaporization phases to allow for a more separated or purified product. Fractional distillation is one of the main operations in chemical engineering. Fractional columns are used in chemical process industries where you distill large, complex mixtures. Industries that use this, as you guys all know, you probably know this better than I do, are petroleum processing, petrochemical production, natural gas, coal tar processing. So many petroleum refining industries use fractional distillation. So like not in the lab, but in a real industrial situation, the crude oil is fed through a feedstock pipe. It is extremely complicated multi-component mixture. Crude oil, like I said, could have hundreds, if not thousands of different chemical compounds in it. So we use fractional distillation to try and separate them into a small range of boiling points called fractions. Because hydrocarbons are so incredibly complex, even using fractional distillations, we still don't get completely pure chemicals. We get what's called fractions. And the last slide I'm going to show you today is something we'll talk about in more detail later, but some of these fractions are listed here. Now, these are not pure, but they're as close to pure as we can get. So the first fraction that would come off at the lowest boiling point would be kind of your LNG or LPG, liquefied kind of petroleum gas. So small hydrocarbons, methane, ethane, propane. Your gasoline fraction would be a little bit higher. So something like C6, C7, C8. Jet fuel, maybe a little even more higher. Diesel fuel, higher again. And then at the bottom, you get some of your really nasty, thick, or the word I should use is viscous products like motor oil, lubricants, industrial fuels, or at the very, very bottom, you get the thickest of them all, asphalt, which is kind of used in, road making. So these are not as pure as we can make in the lab, but these are what we call fractions. And the reason we get fractions is because petroleum or crude oil is just so incredibly complex. Even fractional distillation can't separate it perfectly. All right. All right, cool. So that's it, guys. I went a little longer than I thought, but this is such an interesting chapter. It's definitely something you guys might be more interested in than like naming an aromatic or, cis-trans isomers in chapter 3. This is a little bit more practical for you guys. So tomorrow, we'll look into some of the chemical processes that happen after fractional distillation, like cracking or alkylation. But other than that, I'm good for today. Now, you guys do not have a lab tomorrow morning. Do not show up at 7:30. I will be in bed. Do not show up at 7:30 tomorrow. I know almost half of you have to stay home for self-quarantine anyways, so it's not a problem for you to come to campus. But there is no lab tomorrow at 7:30. We will resume labs next week. So that's it for me today. If you have any questions, let me know. But I'm going to hit stop recording. And if you don't have any questions, have a good day.